This video series is on FEA using Open Source Software Book 1. This is about Case 1, and what we are going to discuss is how quickly can you or we complete a simple 3D analysis using Salome-Meca. So it's a very simple problem. It's a 1 meter cube. So all three directions, the size of the cube is 1 meter. So it's 1 meter high, 1 meter wide, and 1 meter in depth. We are applying 1 megapascal pressure on the top head or the top surface of the cube, and on the bottom surface of the cube we have the entire surface rigidly fixed to the ground. So let's get started. When you open Salome-Meca, it opens in this window format. On the top you have all the default menu icons like File, Edit, View, Tools, Window, and Help. On the bottom you have all the buttons to create new document, to open a document, to save the document, copy and paste. Here in this drop down you get all the different modules of Salome and Salome-Meca that you can select, and all of these modules are also available as the buttons in here. On the left hand side you can see an object browser. On the right hand side is where it's all the 3D modeling. You can visualize that. So you can visualize 3D models, you can visualize the meshing, and when you complete the analysis you can see the results on this big box. Down here you have Python console. Now if you don't need it for the time being, you can turn it off, and you can always get it back at a later date when you can. So this is a very quick video where we are going to create a cube in which on the top surface we are going to apply a pressure of 1 megapascal, and the bottom of this cube, it has the bottom of the cube has the entire surface rigidly fixed. So what we are going to do is we are going to select geometry module. When geometry module loads, we are going to use this standard button called Create Box. It can also be seen from New Entity, Primitives, Box. When you click on it, a new window opens up and it asks for some basic information. It asks for the dimension starting from the origin. So let's enter 1000, 1000, 1000 in all three directions, because we are going to conduct the analysis in which we are going to use millimeters as the dimension or as the length unit. I'll just click on apply and close. You can see partial box on the right hand side. To view full box, you need to click on this fit all button. By doing so, the entire box will be visible to you. Now if you want to use the mouse click and drag, pan, zoom and rotate, right now you cannot do anything even if you do that. So to conduct or to do all of those pan, zoom and rotate, you need to click on the second button here which says interaction style switch. When I click on it and I click and drag the left mouse button, you can see that it is rotating. The box or the 3D geometry is rotating. When you press the middle mouse button or the scroll wheel and move your mouse, it pans. And when you do the same thing, so when you press the right mouse button and when you move left and right or up and down, it zooms. To zoom, you can also rotate the scroll wheel and it will zoom that geometry for you. Now with Salome-Meca or with Code Esther, what you need to do is you need to create some geometry groups. So we can either click on box 1, right click on box 1 and then select create group. Alternatively, you can go to New Entity, Group, Create Group. In Create Group, we need to create surfaces or face groups. So we'll click on the third icon in shape type. For the group name, we are going to enter press it's a short form of pressure. In the 3D view, we'll just click on the top surface, and you can see that the top surface is selected, and the difference is all the other surfaces have black edges, but the selected surface has white edge. Click on Add and Apply. Next, we are going to select the bottom surface, Add, and this is for fixing the entire geometry. Now, when you click Apply and Close, what Salome-Meca does is, by default, the last geometry is visible. To view the entire box, first make this, click on the eye icon, and it'll make it disappear if it is appearing, or if it's visible, it'll make it invisible. If it is invisible, it'll make it visible. So that's a toggle switch. Click on this eye icon and you can see box 1 again. So this technically concludes our creating geometry phase. Next, we are going to create the mesh for the geometry. For creating the mesh, make sure that the geometry that you need to mesh is selected. Click on either Create Mesh button, or go to Mesh, Create Mesh. In Create Mesh, what we are going to make sure is that the geometry selected is box 1. If for any reason box 1 is not selected or it does not come up, it's easy to select it. Click on this curved arrow and select box 1, and box 1 is selected. Next, you can keep the default name of mesh 1, or you can change it to box 1 or cube or whatever you want. I'll keep it default as mesh 1. Next, for the 3D algorithm, we'll go and select NetGen 1D, 2D, 3D. For the hypothesis, we'll select NetGen 3D parameters, and for this simple analysis, we'll keep default parameters for everything. So for max size, for minimum size, and fineness, we'll keep everything default. Click on OK and Apply and Close. After you do that, you are still not able to see the mesh. The reason is, can you see this exclamation mark with a symbol there? It just says that mesh parameters have been defined, but it has not been generated yet. To generate the mesh, we need to compute it. So right click on mesh 1 and click compute. When you do that, the mesh, if mesh generation is successful, first it'll come up with this window which says mesh computation is succeeded, and it'll give you all the details of the mesh, like how many faces are there, whether they are triangles or quadrangles, what is the volume, and what type of volume do we have, whether tetrahedrons or hexahedrons. Right now we have 838 tetrahedrons and all of them are linear. I'll click on Close, and in mesh 1, what you need to do is the groups that we generated or we created in geometry phase, we need to bring them over in the mesh as well. So we'll right click on mesh 1, click on Create Group from Geometry, and in this window we'll just simply select, click and drag on Press and Fix, and they will be selected in Geometry. We'll click Apply and Close, and both of those mesh group would be added to the mesh, or the geometry groups would be added to the mesh. We'll save this file because this concludes creating of meshing or mesh of the geometry that we created earlier. In next section, we are going to see how we generate a command file using efficient software, and successfully we'll run the analysis using Salome-Meca's Esther Study module. Before that, we'll just save this file. I will save this in Documents, Engineering, Video Recording, and in here I'll just create a new one for case1 and I'll save it as case1. So next we are going to see how to generate a command file. For this analysis and study, we are going to use efficient version 0.3 and we are going to quickly create a command file. For the type of mesh, we know that it is an MED mesh and type of calculation is linear static. For analysis type, we know that we are going to conduct mechanical 3D analysis, so we'll just keep it default. For material, the material is carbon steel. We'll give the material name as CS. Young's modulus is 2.1 e to the power 5. Poisson's ratio is 0.3. Density is 7.8 e to the power minus 9, and this will be assigned to all or the entire mesh. I'll click on add to add that to the study. We don't need to create anything for the element type. For boundary condition, for the type of boundary condition, it will be degree of freedom on mesh group. Boundary condition name we'll give is fix, and this boundary condition would be assigned to the mesh group of fix that we created in Salome-Meca, and we are going to say that all 3 degrees of freedom in X, Y, and Z are restricted. We click on add. Next we are going to add load, or we are going to add pressure on the top surface. So the load name is press, PRESS, press. The load type would be pressure. It is assigned to the mesh group of press, and the amount of pressure is 1 megapascal. I'll add this to the analysis, and for the output we just need to get the von Mises stresses. So I'll just add SIEQ NOU, which gives us von Mises stress. So I'll select that and click on add. Next I'll click on save command file. We'll quickly go to document, engineering, video recording, case1, and we'll just say it is case1.com and save it. It gives you a message that writing of command file is complete. Click on OK, and that completes the generation of command file. Next stage of analysis will be carried out in Salome-Meca. So now we need to select Esther Study in the drop down menu, and Salome-Meca will start Esther Study, or it will load Esther Study. Once when it loads it, what you need to do is, in the current case, right click and click add stage from file. This is the command file we just created recently, so we'll select it and click on open. Esther Study gives us a message saying that there are some undefined files. The undefined files for us are the input and output file, and I'll show you quickly how to add them in. The mesh, we haven't selected or told Salome-Meca what mesh this entire analysis needs to be done on. So double click on mesh here on the left hand side in data settings. On the right hand side in the edit command section, in the mesh file location, click on the drop down and select mesh_1. When you select that, the entire mesh would be visible in this middle window. Click on OK, and that will add mesh 1 for the data file. The next one is the output file, which is not selected, or the location of the output file. Because there is no output file selected previously, we'll need to click on this button with 3 dots and give it a name and a decent name with med at the end, or rmed, to suggest it's a result file. I'll just say it's case1 rmed. Save it and click on apply. So here we see that mesh 1 and case1.rmat, both are selected. For the next stage, we need to go and click on history view. In the current case, case 1, click on this plus sign which says it's run, and then click on run button on the bottom side of it. When you click on it, it says that this operation needs a study directory, so you should save study before executing this operation, which makes sense. So we'll first click on save button and then again click run. When you do, Salome-Meca would start its analysis, and you can see that this hourglass is spinning, which means that Salome-Meca is working in the background. Now auto refresh is set to no. Instead of that, let's put auto refresh on 5 seconds, and as you can see, the Salome-Meca quickly said that the analysis has been successful, and it shows you a green dot, which for Salome-Meca it means that the analysis was successful. To view the result, we click on in the data file summary, click on case1.rmat, right click, and then click post process. When you click on post process, Salome-Meca goes in the background and loads ParaView, or a version of ParaView which can read MED files. Here you can see a really nice colorful view of the analysis, and this is the color combination of deflection or displacements. The components are magnitude, so this is in X, Y, and Z. You can also select dx, dy, dz. We are going to select magnitude, and as you can see, the scaling factor, so this is deflected shape. The original shape, you can see it's transparent here on the top. To see it a bit in more detail, you can increase the scale factor. Click on apply, and as you can see, this is when you increase the scale factor to a large number, you will see the deflected shape. Now the original shape is again in transparent box, and this is the deflected shape. Now the deflection is very small. It is 0.0047 millimeters. So 1 megapascal on pressure on top of a 1 cubic meter of steel block, it gives very minor deflection. To see the equivalent stresses which are interpolated, and specifically von Mises stresses, you click on the in the result field, you click on SIEQ NOU or equivalent stresses, and this will show you the equivalent stresses. As you can see, the stress on the top surface is 1, which again in this is in megapascals, and on the bottom it is virtually 0. Now the reason for uneven stresses is because the bottom surface is rigidly fixed. Now if you want to see even deformation and even stress in the entire cube, we'll have to do something different. So this is how you conduct the analysis and visualize the results in Salome-Meca. In this video, we just saw how easy it is to conduct a three-dimensional finite element analysis using an open source software, Salome-Meca. The version was 2019 for Salome-Meca, and we just saw that the pressure of 1 megapascal on the top face or surface generates an uneven stresses in the entire block. Now I'm giving you a homework sort of, if you think, or example or a worked example that you work by yourself, and you can send me the screenshots either in the comment section here, or send me as an email, and I'll have a look at them. Conduct a finite element analysis of this 1 meter cube with pressure of 1 megapascal on top, but change the degrees of freedom of the face of the bottom face somehow, so that the entire cube has the stress of 1 megapascal. Now what to do, how to do it, I'll leave it up to you, and you need to tell me how are you going to get the stresses of 1 megapascal in the entire cube.